Welcome to Constant Variables, a podcast where we take a non-technical look at building and growing digital products. I'm Tim Bornholdt. Let's get nerdy.
Welcome back to our Oofda series, sponsored by the Jed Mahonis Group. In this series, we're giving you a bite of what you need to know about a technical subject, introducing you to an expert in the field who you can follow, and linking to resources where you can dive deeper. In the coming weeks, we'll have episodes on APIs, serverless, machine learning, agile, but first, quantum computing.
Hey, Alex, welcome to the show.
Hey, Tim. Thanks for having me.
I'm really excited to have you on the show to talk about quantum computing because, we were kind of talking a little bit beforehand, and this is an area where I've been long interested in learning about it, and it just seems so overwhelming. So, tell us about your journey into quantum computing. I feel like we should be able to trust you in this area, right?
Yeah. Oh, actually, trust is a good thing to talk about because I'm going to tell you things that are not going to be so mainstream. But actually, I want to shake up a little bit the mainstream, but I'll tell you exactly why and how. So I'm not an active quantum computer guy anymore. I did my PhD in quantum computing, though, in quantum optics, working with single atoms and trying to make them dance with lasers so they act like a quantum computer. Now, that was 4 or 5 years, really, graduate work. And after that, I changed to automotive industry, designing camera systems for advanced driver assistance systems. And then I used my optics skills, but not really my quantum mechanical skills, apparently, anymore. And I did that for 7-8 years. And then I switched back to academia, where I'm now a professor of physics at the University of Applied Sciences in Duesseldorf. And there I still don't do quantum computing. But it is, a PhD is a bit above your baby. It never leaves you, right? It's grown. And but I look in on it all the time. And I try to convey quantum computing because I think it is important to people, lay people, actually. So I was really glad about this opportunity here. I've written 3 articles for a very popular German computer magazine. I've given several talks to the public about quantum computing. So I've tried some stuff. So let's try some new stuff today to see really focusing on non-technical people and still getting out the gist of quantum computing.
I just love that you traded up from one complex problem in quantum computing to another one in computer vision. That's so fascinating.
Yeah, and I love it. Actually, it was a hard lesson for me to learn when you are so focused and so really geeking out on a single topic. I did quantum computing and nothing else for 4 years. And kind of at that point, it feels unreal to do that. Any other problem might be interesting as well. So I left academia with, okay, I'm always going to regret this a little bit, but it's the right decision. And not only was it the right decision, but I'm a lot happier than I would have thought. And I much enjoyed this challenge and image quality as well, and now I'm enjoying it a lot because it's my research focus.
I love it.
Yeah.
Well, good. Well, so at the very least, like I said, we are talking to somebody that might know a thing or two about quantum computing here.
Well,
so
I think hang on. And here's the thing. So because I'm not active in the field, I think I'm actually, that's pro and con. So it's good because I see more of the wood, and it's not so good because I can't explain you every single tree right now. But when I was thinking about what we could talk about in this podcast, I actually thought this, seeing the wood might actually play into our hands with a bit of distance, a bit of critical distance to what's out there, because it's really a tremendously hyped topic.
I agree. So, let's jump in. So,
Yep.
I think maybe people have heard of quantum computing, maybe they haven't, but I would love it if you could give us just an explanation of the trees, like you said, as you see it from the forest level. How would you explain quantum computing to a non-technical person?
Yeah. Well, really, we need to. You can't really explain it, okay? That's unfortunate. Okay, but hang on. We are not going to do the usual, this is a qubit and this is a superposition and parallelization and that makes it fast. We're going to drop all of that because it takes many years full-time training to be able to make your own, not decision, but to be able to, what's the word I'm looking for?
Well, to be able to keep it in your head of like to visualize like what's going on.
To critically reflect on new concepts, so like a working knowledge. Yeah. So that takes many years of training, and so we're not going to try to compress that in 5 minutes. But what we can do is, well, what can the machine actually do? So let's think about the quantum computer as a black box, and we will ignore for this podcast how it works, but we will try to understand what's exciting about it from the application side of things. And I also think that's more interesting for the non-technical people. And there's a lot to learn about that. And so there's one thing I would like to explain, and that is a bit technical, but that is how do we measure the speed of a computing machine, regardless if it's classical or if it's quantum mechanical. And so bear with me a little bit. I'd like to give a brief example how we measure the speed, and then we can judge the different applications by, hey, does it offer a better speed or not? And interestingly, I'm going to tell you that, okay, Google showed that their computation was 10 million times faster than a supercomputer. And I'm going to tell you, well, that's not interesting. But and why that is not so hard, that's exactly at the heart of quantum computing. So let's try to go down that route. I'll try to explain how we measure the speed of computing systems, and then we compare classical to quantum computing applications using that measure.
Perfect. Let's do it.
Okay. So we measure computing. So suppose you have a large computer with 1 million processes, and it only takes a microsecond to calculate something. Now, this whole operation might take on your desktop PC, which has 1 CPU, 1 second, right? So the supercomputer is 1 million times faster, and one takes a microsecond and the other takes a second. But that's not faster, right? If it's the same algorithm just being run on 1 million cores, you wouldn't say that the algorithm itself is faster, right?
Right.
So an algorithm is counted by the number of executions it takes you. Let's take an example. You look up a phone book, and let's say the phone book has 1 million entries. Now, if you just start at the beginning and you just look through the whole phone book, it takes you on average about 500,000 lookups to find the right person, right? I mean, sometimes you get lucky and it's only 100. Sometimes you have bad luck and it's 999,000 before you actually find the name you want to look at, right? So let's say it's a 500,000 lookups. Now, if you jump to the first letter to the correct section, and then jump to the next section, right, using the second letter, and then the third, and you get to the hit very, very quickly, right? And here's the single bit of technicality I'd like to give. So you need to take it from me. The first one was 500,000, and this one now scales with a logarithm of the number of entries. Okay, please just bear with me and use it. Yeah, but Tim, how else could I say that, right?
You're right. I'm tracking with you. Yeah, that makes sense to me.
Cool. And because that's 1 million entries. It takes algorithm 1 takes 500,000 times. Algorithm 2 takes the logarithm of 1 million is 6 times, because it's 6 zeros in 1 million. It's 6 times. Okay, so 6 to 500,000. That's a lot. That's a good speed up. But using a supercomputer we talked about before, the 500,000 lookups, if you do that 1 million times because you got a supercomputer, you might still do it in 0.5 times. So you might even still be quicker than the 6. And that's exactly what I'm meant to say. Now let's scale it up. Let's say the telephone book doesn't have 1 million entries, but 1 billion entries. Now you have to look it up 500 million times. Now, in the logarithm example, it has 9 zeros, so you have to look it up 9 times. You see, 500,000 to 6, 500 million to 9. Now, 500 billion to 12, 500 trillion to 15. You see how that scales? The one is just going off the scale and the other is just, increasing nicely a little bit. Now, this is how we measure computing speeds. Because we want to get, I got a larger GPU than you. We want to get that out of the equation and actually compare apples with apples, right? That's how computer scientists measure the speed of a computation. So let's let that sink in a little bit. Does that make sense so far?
Yeah, so just so I can make sure maybe the audience and for myself, if I restate that back. So let's say let's say we had a list, because phone books, maybe there's some younger kids who don't know what a phone book is. Let's say you have
oh, sorry, I forgot that.
I don't know. Maybe I think everybody knows what a phone book is. But if you have a directory
of players in Fortnite.
Yes. There you go. So if you have this giant list of people that you're looking for, if you do it, there's many ways that you can find what you're looking for. You can go every single one and go in order until you get to the one. And that's the approach that would get you, if you had 1 million people, it would take you on average 500,000, because sometimes you might have Alexander Abramson, which would be very close to the top. And then you might have Zachariah, whatever, way down at the bottom. So sometimes it averages out to be about 500,000.
Yes.
Of a list of 1 million. And now what you're saying with doing it, the approach of, if you know the person's name and you're doing a lookup, you can start with Z. And if the person's name is Zachary, you start with the Z. So you already have limited the amount that you have to search for. So you drop right down to Z, and then you do ZA, that lowers it even further. And so you end up being much more precise with getting to it. So what you're saying is, if you make that list, instead of 1 million people, 1 billion people, or a trillion people, the approach that you're taking, where you search by the name and the letters, and you go each individual letter and you sort that, go in order, it's a lot faster to search that way and do that computation to get to the right answer, as opposed to doing it the other way, where you start with the very first A and you go down the list until you get to your answer. Is that right?
Yeah. Exactly. That's exactly right. And now mathematically, you can really write that down and make it very precise, so you can actually measure speeds. And that's what you do when you compare classical computers to quantum computers. And now this 500,000, 500 million, 500 billion, we call not feasible as computation. And the 5, 6, 9, 10, 12, 6, 9, 12, 15, we call that feasible computation. Okay. Now, when we talk about exponential speed up, which you hear a lot in quantum computing, it's exactly this difference. The one scales just linearly with the number of inputs, and the other only with a logarithm. And that is the deciding difference, right?
Got it.
It's this scaling. And that's what we're going to get back to again and again. So, and that's and now we can actually talk about applications, right?
All right,
we've got the basis. So why all this excitement about quantum computers? In 1994, Peter Shaw presented an algorithm that showed just this change in computing speed, and we call that a complexity class, right? How complex is a problem? He showed that he could factor prime numbers in an exponentially faster complexity class. So he had invented a new novel algorithm that went from the 500 million to the 9 operations for prime factoring. And now you say prime factoring, I did that in elementary school. It's a long while. Okay. That's not what's interesting. What's interesting is that if you can do prime factoring, you can break all current encryptions, because all current encryptions are based on prime factorization. So he invented an algorithm that breaks all encryptions. Now that made quite a splash. And basically we are still living off of that promise. 1994.
So, right? Describe that for me. We're living off of that promise. What does that mean?
that we don't have it, and I don't see it happening anytime soon. And that's but we really need to understand this difference between how you do the computation. So now he has shown theoretically, I can make a new device that has an exponential speed up that is in this awesome complexity class. But it takes a quantum computer to do that. Again, we picture quantum computing now here as a black box where you insert numbers and you get a calculation out with the result. So if we had that hypothetical device, then we could do that. Now, the problem is building one is exceedingly difficult because of quantum mechanics. And you might have heard that in quantum mechanics, if you look at an object, its wave function decoheres and collapses. I'm not sure if you've heard that. Schrödinger's cat, for example.
Oh, yeah. That's where it is Schrödinger's cat, where there's you don't know whether or not there's a cat in the box until you've opened the box and looked at it.
Almost, very close. No, it's the cat might be dead or alive.
That's it, dead or alive. That's it. Okay.
And but again, at this point, I'd like to make a little commercial for a book. So again, let's not go down this rabbit hole about trying to understand what quantum mechanics is about. And if you are interested in these types of things, I highly recommend the book Beyond Weird from Philip Ball, I think he's called. Philip Ball or Philip Glass? No, Philip Glass was the one with was the author, the fantasy book. Beyond Weird, it really explains in everyday language all the complexities of the concepts of quantum mechanics. Highly recommended. I like it a lot. Okay, now here we're going to go back to application. So you need to build a quantum computer. Quantum computer is hard to build. And even today, we are far, far, far away from a quantum computer that can run Shor's algorithm for any sensible size of problem, right? So if you have a usual, even small 256-bit encryption, which is considered quite normal today, it would take millions of qubits to actually solve that, to run that algorithm. And we are so far away from a million qubits that we don't even see how to get there. I mean, people claim that all the time, but I'm a bit skeptical here. So that's the big promise and where we stand with the big promise. Okay?
Got it.
And but there are many different aspects to it. So I've thought about this a little bit before, and I'd like to classify that actually into three categories. When we talk about what applications are feasible for a quantum computer, let's talk about three categories I'd like to put to you. So the first is called a universal quantum computer. That's the one that runs Shor's algorithm. That's the one I've been talking about right now. And that's the one that operates with single qubits and it's with gates on single qubits, like you have 0 and 1 gate on a traditional computer. Anyway, sometimes this is called nowadays a gate quantum computer. The ones from Google and the ones from IBM and the ion trap quantum computers, those are universal quantum computers. So that's category one. Category two is what Feynman envisioned in 1982 as the original starting point. He said, let's make quantum simulators. He was at a physics conference and they noted, hey, it's darn hard to calculate the wave function of any quantum system. And he turned that around. He said, well, if it's so darn hard, such a complex problem to calculate quantum systems, perhaps we can use other quantum systems as a simulator to simulate the problem that we actually want to research, right? And this is what's happening. We call that a quantum simulator. That's category two, quantum simulators. And the third one is what I would actually not call a quantum computer at all, but here we are leaving mainstream, okay? I need to really highlight that this is my opinion that is not mainstream.
Sure.
So you might have heard that which they call a quantum computing device. It's called a quantum annealer. I'm not sure. Have you heard that? Probably not.
No, I haven't.
Annealer. Okay, so quantum annealer has been around for a while now, and there's a company, D-Wave, who makes those systems, and they claim that they have a nice quantum computer with 5,000 qubits, which is a lot more than the 53 Google is having or 74 IBM is having. And I'm not entirely sure how many qubits we have, which is Google or IBM, which is the largest, but it's below 100 or around 100 qubits. Okay, so it's really a low number. And now this company claims, and has been claiming for many, many years, that they're working on 5,000 qubits. Right. And I'm going to talk to you today and say that, okay, this isn't even a quantum computer, right? It is because of complexity class. It executes a classical algorithm, it computes a good algorithm for traveling salesman problem. And traveling salesman is it's a combinatorial problem, as we call that. It might also, if you want to optimize a traffic simulation, how many traffic participants you have in a city and what's the fastest route, or you have a warehouse and you want to do logistics, all this. Okay, how many times can I arrange 5 different boxes? That sort of thing. But it's a classical algorithm. So the end application is a classical algorithm, and it uses quantum effects to accelerate that classical algorithm. But here's the rub. It still remains in the 500,000, 500 million category, right? It is executing a slow classical algorithm. It accelerates that like our supercomputer, but it only accelerates the number of processing units you have, right? That's about it. It doesn't speed up exponentially. And that's why I say that the quantum annealer is not a quantum computer. I know people who said, I don't care about this exponential speed up. If the machine is 1,000,000 times faster, it's 1,000,000 times faster, I'll take it, right? And which of course has its merit, and the quantum annealer can do that. But I'm convinced if it only parallelizes, then it should be possible to do that on a classical machine as well. And therefore, a real quantum computer, in my definition, is that one that you can never do on a classical computer, no matter how smart, no matter how good.
Man, okay, so there's a lot to unpack. but no, that is I think that last point that you made is kind of where I've gotten to with quantum computing, of like, and why it's still so theoretical. Because like a lot of times people do think that you can just, if you stack 1,000,000 computers next to each other, they're just it is 1,000,000 times faster, but that's not quantum computing. That's just you've added 1,000,000 workers to solve the problem, and you still have to reassemble it back into one.
But the problem is still the same size.
Right.
That's exactly it.
And so quantum computing, and maybe this is where I could get more clarity too, like doing it where you're just parallelizing, which in another term is saying you're taking 1,000,000 computers and running them all at the same time, doing the same task.
Yes.
True quantum computing would be moving from when we had that example of looking up 1,000,000 users and you're going through it in from top to bottom. Quantum computing is flipping it so that it's using a logarithmic approach, where it's jumping and doing things faster. Is that truly doing it faster, and not just taking the process of going through it one at a time until it gets to the right answer, but like truly legitimately making a complete fundamental shift in the way that you go about computing that answer.
Yeah. That's exactly right, Tim.
Okay.
But again, this is not universal, right? I say, because I want to make the definition quantum computer needs to have this exponential speed up. Then the quantum annealer executing a classical algorithm is not a quantum computer, right? But it is using quantum effects. That's okay.
Yeah, and that's what kind of makes this whole area a little difficult from a non-technology standpoint to understand is because it's like, especially when you, I mean, you've worked with nerds in your day, I'm sure. And I'm one as well. Like, we're all nerds. And so words matter and semantics matter and definitions matter. Like you have to be clear and articulate of what you're trying to get across, because at the end of the day, I think a lot of times the reason people don't like technology and don't like technologists is they just have a problem they want to solve. They couldn't care less about the how it works.
Yes,
they just want the thing to work. And that's the thing, like with quantum computing, like there are quantum effects that can benefit all of us. And true quantum computing, like it is such just based off of your explanation here again, and kind of thinking through the problem in my head of like, if we had true quantum computing, that would unleash a host of new solutions to these problems. Like I was just thinking of what I wanted to go back to and touch on a little bit was the problem you were talking about, encryption, which is like a whole nother kind of episode we could go into, but just the problem of finding the prime numbers and being able to crack a complex encrypted message. The only way you could do it now is just like you said, if you lined up some really powerful computers and let them run for 1 million years, they'd be able to crack the solution. But if you were to put them into a quantum computer, it would be able to just solve the answer, because it'd be able to use a different approach of getting to the answer rather than doing how we're programming computers to work in from 1 to 2 to 3 to 4 to 5 to 6.
Yeah, exactly. That's it. Unfortunately, we don't have that quantum computer, that universal quantum computer. So in practice, now looking at the application side again, what currently is mainly is happening also is on the second step, the quantum simulations I was talking about. Yeah. And I think that's really where the application right now is ripe for some cool scientific progress. Quantum chemistry, for example, right? How do molecules form, right? Because that is a really hard quantum mechanical problem. It's just not feasible, as I said before, right? It's really, really hard to calculate. Now, if you can make a quantum simulator that simulates a different quantum system, then you would understand quantum physics better. You might be able to develop novel drugs or medicines. And because, this sounds very technical, but if you can find the energy levels of a molecule, then you know what it does, basically. And all of this, finding energy levels exactly, is technical term for, I know how it works, the molecule, and I use that quantum simulator to find novel molecules, to find novel solutions. And I mean, in polymers, in medicine, right, in pharmaceuticals, all there I see very interesting applications that might be doable by quantum simulation right now. But and I'd like to mention here, the quantum annealer can be used for quantum simulation. So it is officially in category 3, but it can be used for category 2 as well. And now I think they are moving into that direction to really look for application that their annealer can solve now. Yeah.
Maybe this is like a weird question, but one thing that I'm trying to wrap my mind around with this is like, it seems, just correct me if I'm wrong, but what it feels like is quantum computing is like we're trying to solve a problem that we don't quite know how we're going to solve it. And we need is that kind of like with the simulations that we're running to try to unlock how we would build a universal quantum computer? Is it that we're trying to simulate possible answers in order to get to the actual answer of how we could build a quantum computer?
For me, that's part of it, because one of the reasons why it is so darn hard to make a quantum computer is, well, first of all, it's just basic quantum mechanics that we really understand already well and have been for 100 years. It's the decoherence and the collapse of the wave function, etc. But when you look one step further, how these qubits interact in a quantum mechanical manner, and how now I'm going to drop a word here, entanglement. They get entangled. Just imagine a spaghetti soup, right? Forming one large wave function that does stuff together. And yes, I do believe what you just said. We need to understand it further, and I think in this understanding multi-particle entanglement, quantum computers can help right now, and that's where a lot of the work is going. And again, quantum physics, quantum chemistry, then is a part of that. Really, it's multi-particle quantum physics, if you'd like, with a twist of, okay, let's do large molecules so we can do chemistry.
Man, yeah, this is one of those areas where you do really need to get into the trees to really understand like all the different components that will get you to be able to pull back and show. I mean, like, because I think at a high level, the easy answer to what is quantum computing and how can it benefit me is like, well, it's basically fundamentally changing how we do almost everything with technology these days, and makes it way faster to execute. But it's also one of those problems that we have so much to still understand, and there's so many little aspects to it that we just. I'm trying to think of like, I guess that's where my question was going to go. Was you mentioned a couple of experiments or a couple of things that we still need to answer. Are there like, how do you know at all of like, or having a handle around what kind of experiments or what kinds of problems people would go about to go and figure out how to get closer to the universal quantum computer?
No. No, I wouldn't. It's like I'm kind of waiting for the transistor moment of the classical computer, right? When in the theory was all there for classical computing, right? Set up by Turing, and I think 36 was the year of his PhD thesis, or 38, where he published the Turing machine, and everyone's been waiting just for the transistor really in the 50s. And then it hit off. And we're still looking for that. Right now, it's mainly a technical question, how can we solve that? But this is a gut feeling here. We run into the same walls no matter what technical system you try. If you use ion traps, if you quantum flux bits, if you use diamond defects, right? No matter what, it's always this. So I'm kind of guessing here. Really, there is a fundamental reason, and we need to understand multi-particle entanglement better. And in that sense, I think you have it's called technical, right? Let's make just a transistor, a qubit that is like the transistor of the future. But I'm not sure if we can get there at the current level of knowledge about quantum physics. So. Well, who knows? But there's one thing I'd like, and yeah, you mentioned something at the beginning of your question. I'd like to briefly go back to. So now, a universal quantum computer is a universal in that it completely includes all classical computations. Okay.
Okay.
That's just basically part of the parcel. But the level of classical computing we have these days is just, unbelievable. We are never ever gonna replace our normal PCs with all quantum computers. I just can't see that, because it's so difficult to make a quantum computer. I mean, perhaps 200-300 years in the future, but really, our classical computers are going to stay, and we will have, for certain applications, we're going to have speed up modules, like you use a GPU today. We're going to have speed up modules that are based on quantum computing.
Well, but, that makes sense.
Yeah, it's not going to completely replace classical computation, because we are really good at that already.
Right. And because classical computation solves so many of the problems we have just in and of itself, quantum computing is just, it allows us to unlock a whole nother level of problems that we can solve. And
yes.
I think one question that I had around that is, I've been 2022 is my year of understanding hardware and being better with understanding how hardware works, because I've always been super intimidated by anything with like a circuit board. And I mean, I've built my own computers, and I know how to I can work with Lego. They're basically Lego blocks at that point to me. Like exactly. I know how to plug a PCI board into a slot and call it a day. Right. But
that's good.
But like when you say the word transistor, I'm like, okay, I have a vague understanding of a transistor, but I think if I'm sitting at that point thinking like, what the hell is a transistor? You lost me 5 minutes ago. Could you give me like just a brief analogy of like what the transistor actually does in classical computing?
Yeah, we can do it even easier. It's very simple. It's just the little technical unit that contains 0 or 1 and exactly 1 bit.
Okay, that makes so it's either on or it's off. It's 1 or 0.
Exactly, and it's a little bit of a simplification, but it's on or off, and and we just take billions of those because we can make them very small, put them on a processor, and then we have billions of zeros and ones to work with, and we combine them electrically in different manners. So one is adding, one is subtracting, then you have a logical gate called XOR and whatnot, right? And then suddenly you can snap a picture with your phone, and it's displayed on the screen, and that is just done by billions and billions of transistors, because every single transistor has a 0 or 1, is a single bit. That's how we picture that.
I want to take that last 30 seconds of what you said and print it out and put it on frame it somewhere so that I can always look at that and never forget. Because it's okay, like, cool. I originally was going into computer engineering for my degree, and because I really just wanted to work with software, and then all this it entered in where engineering, you actually need to understand transistors and how all of this stuff works. And for me, it was just like, I don't know, I hit some sort of mental block. So this, to me, it's like, I wish that somebody in my freshman physics class would have just sat down with me and explained this in that simple of terms. And that's like what bothers me so much about our industry and like what technologists do to each other, where it's like you get you this is like the foundation, and the foundation stuff, like once you get really into it and you understand like what those possibilities unlock, it's so exciting that you just kind of forget that most people get stuck at that first step of like, a transistor just it turns on or it's off and that's it, and then you lay a billion of them next to each other, like that. Just even that like made the analogy before of like when you're researching through a million records to try to find the right one, and you're going in order. It's like that's basically what the computers are doing these days, where quantum computing, it's not just having a resistor turn on and off to get to that point, it's having something else work that gets you to that solution so much faster, but we just don't know what that something else quite is at this point.
Well, actually, but I need to comment on that as well.
Please do.
So first, the transistor alone is not the 0 or 1. That is already a simplification, but here it is a good simplification, I think, to make that clear. And I forgot what I wanted to say next. Okay, never mind. It'll come back.
That's okay. That's okay, because I think with just even that, it's like I know my analogies and my understanding of this isn't perfect, and that's why I love having this series on our podcast, is because I feel like a lot of times I bring on guests in my comfort zone where I can tee up easy analogies because I've thought through all of this. Where this is like I feel like I'm learning on the fly with I'm sitting with a professor actually learning this on the fly. It's pretty awesome, and I get to have an audience joining along with me, yelling at me for how dumb I am of not getting it right out of the pan.
But hang on. Okay, now this brings me to a larger topic. I'm really glad we're doing this. And no, you're not stupid, not at all. And no one who does not understand quantum mechanics is stupid, because it takes years and years of mathematical and physics training to get to the point that you can actually, start to really grasp the concepts. And what bothers me is I see that technology has so far advanced that it's so remote from everyday experience. That it's a problem, right? That it's Feynman could explain quantum electrodynamics to the lay people, but even him, it took 5 or 6 sessions, 5 or 6 evenings, right? And he was one of the biggest geniuses we had in the 20th century, and we did have some really good 20th century physicists, right? And Feynman is among the top 3 at least, right? For me, he's the best, and I'm not that genius. Almost no one is in the whole world, but we need to get a grasp and to make it less remote, right? I mean, I'm fundamentally concerned about how people ignore scientific facts, because it is so easy these days to just, I'm just going to throw something up here, which is complete bullshit. Sorry for the word. You can beep it out. And, but it takes years and years to refute, because to do it correctly, it's difficult. And like in this, if I told you anything wrong, right, you wouldn't have a single chance to correct me. And, I'm worried about that. I think this translation from technology to the lay people is really important. But this is a first-class example how difficult it is, and possibly even impossible, right? You cannot form your own opinion of quantum mechanics unless you studied for several years, and that's not good. So, but I don't have a solution right now.
No, that's Yeah, that's exactly why I love this podcast and why I'm so glad you're on this show, because that's such a great point. Like there's so much about technology that like I think just like you said, like in the greater scientific community, I mean, you can look at things like vaccines or even something as stupid as like the world is flat. Like it's so easy to refute that on so many levels, yet there's a thriving community of misinformation. And I mean, that's one reason why I harp so hard on people understanding how Facebook works and how their business model and how the news works. Like all of it's like it's not like this conspiracy theory insofar as people are trying to distort your worldview. It's like the people that are trying to distort your worldview are trying to make money off of you. Like there's nothing wrong with learning new things, with changing your mind, with growing your perception of the world. Like there's nothing, the only danger in that is that any entrenched incumbent of that's making money or gaining power off of your ignorance, like they're going to refute you wanting to go and do that. But for me, it's like, why would we not change our mind in the face of new evidence and in the face of people that, like you said, people are spending
because it's
years
hard
and decades. It's very hard. It's very hard to change your mind and to change your perceptions on things. But that's something we really have to do.
Yeah, that's the thing I really can't wrap my head around. Why is it so? But that is the core of the problem here, right? People think that they can form an educated opinion reading stuff up on the net, right? And I'm sitting here telling you cannot do that. You cannot do that for quantum computing, and probably not for the new vaccines. And there are just so many. But that's what I mean by when I say that the modern technology is so far advanced, it's so remote from everyday experience that you cannot form an opinion just by sitting down and like reading up a little bit. And still we do this podcast because it's good to have the people appreciate at least a little bit how much there is beyond certain technology, right? And how much more there is. But sorry, I'm rambling a little bit because, I have no solution how we are going to cope with this. But I think doing this stuff here, trying to make people have fun learning new stuff, appreciate the depth of a certain technical topic, it's at least the first step we can go. And that's why we're doing it, right? Even if it's basically an endless road.
Well, I think it could come down to like there's just the way that the world has shaken out over the last few years, especially. Everyone is just growing so distrustful of each other, and I think there's just no way that you can learn everything about everything. It's impossible. So you have to be able to rely.
Not learn. Sorry, Tim, but now you can not even learn everything about one thing because when I had my PhD. When I just finished that, I was expert in the very, very niche field of quantum computing with ytterbium ions and not even calcium ions, right? And that's already one step advanced. But that shows just how crazy this is.
Yeah.
Right.
And that's what kind of going back to you were saying how we're in such a weird state of things. It's like you used to be able to say like, hey, Alex, give me an idea of how this stuff works. And you'd say something. And just like I did on this podcast, I take your word for it because you're the one that put in the time. Like it's proven that you've had your peers who are experts, like have bestowed upon you the title of doctor because you have done the work and you do understand this thing. So it's like you have to, there's just this like fundamental distrust in systems and in processes and in things. And it's like, how do we move forward from that point? Like there is no good answer, but that's where I'm trying to get to, like, even at a small level with a podcast like this is I can at least talk to a couple hundred people and people who trust me in one way. Like we're going out and we met you through mutual connections and we've built a trust up of, this guy knows what he's talking about. And we have to get back to like, as great as it is to be global, like it's global because I'm talking to you 8 hours in the future. Like you're 6 hours in the future. Like you're off. Yeah, it's it's great to have that global perspective, and it's like we still have to find a way, like, for the internet to build that trust with each other, and be able to implicitly understand, like, yeah, you've got my best interests, and you're not going to like purposefully throw some weird quantum computing term at me and lie to me about it. Like, you're telling the truth, and I trust you, and we have to figure out how we can get back to doing that in a digital, quote unquote, metaverse world. I just kind of threw up in my mouth saying that, but you know what I
mean. That's it. I think I know the solution. What we need to do is we need to have a church of facts. And
yeah,
because you just said it, either you believe me because you like me, or you don't, right? Because you don't like me. And this is how we humans make decisions. Look it up. I mean, have you read Daniel Kahneman's Thinking Fast, Slow?
Yeah.
Yeah. So, I mean, that's just how we're wired, right? And if we could make a church of facts and make it transparent, what we want with that is, because fundamentally, and I don't want to be in a, I think you can believe everyone has a spiritual desire, need, and that's not what I'm talking about right here. Even when I use the word church, please, everyone go to their own beliefs and stay there. That's fine. But I'm saying in my church of facts, I can point to, and this one made an experimental observation based off of that one, going back 400 years, all the way to Tycho Brahe, who did the first Mars observations, and then we understand that the solar system revolves around the sun. I can go back 400 years and saying this one rests on this, on that, and I believe that person really did an observation. You see, that's my belief, and people need to believe it, because you cannot possibly read all the stuff and comprehend it. So it is a belief system. So I don't know how to go on about that, but that could be one way of tackling that, taking our special wiring into account.
That's exactly. It's always like we have such dumb monkey brains in so many ways, but it's like, and it's so crazy how this technology of the last, call it 100 years, like it's technology has evolved at a pace that our species has never seen before, and it has enabled us to do so many things that we've never been able to do before. That we have not even begun to cope with the consequences of that. We've only found ways to pervert it and satisfy our basal instincts with just endless amounts of entertainment. Well, you know what I mean. But that is something that we still have to cope with, is like, okay, we have this ability now as a species. Like, are we just going to use it to nuke ourselves to death, or are we going to use it to find ways to better our species, better our planet, better our universe, more fully understand our universe? Those are the problems that I'm more interested in understanding, and it just sucks that I have to spend my time telling somebody that the Earth is not flat, or that we actually went to the moon. It's like I'm sick of wasting time on those problems where we could be having more cool conversations like this.
Yeah, but let's be positive. I'm in general an optimist. Now, the way I see it is, all this new technology holds a mirror in front of us, and basically on almost every single decision, you are being told, but you're being irrational. Yeah, because we humans are irrational. And the more we learn that, I think the more, people don't like to be told you're being irrational and that's stupid, right?
Yeah.
But we are fundamentally wired. This is explicitly shown by Factfulness, the book Factfulness. Have you read that?
Mm-mm.
Okay, cool. Factfulness by Hans Rosling. And he demonstrates the bias we have innately embedded in our brains. So especially if you've read Kahneman, you're going to enjoy that one. And where was I? So this new technology holds a mirror to us and saying you are being irrational, and we don't like it, right? We don't like recognizing ourselves that we are wired the way we are. Like, a lot of people are not, all right? Because we are thinking we are rational. Remember Kahneman. Now, but let's now put this in a very large context. In the beginning, we see with our own eyes that the Earth is flat. So that being curved is just so insane. We don't want it. Let's burn you at stake. Yeah, that's a good idea. Hey, do you agree, John? Yeah, let's burn him at the stake. Woohoo! Okay, good. So, right. So the first one is burned on the stake. And then there is experimental evidence that kindly filters through that, okay, perhaps the Earth is not flat, but it's actually a marble. Okay, right? It's a ball. It's a sphere. So, but at least the sun revolves around us. I mean, look up in the sky. I can see with my own eyes, right? And but that's not what happens, right? We revolve around the sun. Tycho. I'm not sure how to pronounce that in English. Tycho Brahe.
Yeah.
He's the one.
That's how I've heard it.
Okay, that's the mentor of Kepler, and he said, "Okay, come on, guys, let's stop talking about this. We've done this for a couple of 100 years. We burned a couple of 100 people. Okay, now let's just experimentally look at it. Okay, I'm just gonna stop talking, and I'm gonna prove that the Earth is in the center of the universe. No questions asked." So he sits down, he records day after day, night after night. Well, not on the day. He's observing the Mars. So night after night, freezing his fingers off, and more his PhD students, right? And he does that for decades, these large books. And then he dies not accepting that the sun is in the middle of our universe and not the Earth. He has to die because he can accept that. And then his student and mentee, Kepler, goes and says, no, look at the data. Look at the data, which is really precise. The sun is in the middle. And with the advent of modern AI, so now I'm going to skip to today, with the advent of modern AI algorithms, we understand just how irrational we are in the Kahneman sense, right? We are having another... I don't believe what my eyes are telling me. I believe only what my eyes are telling me and not what science is telling me, right? And I think that's a really fundamental conflict. Now, we've managed the last two well, so let's be positive for the future. Let's hope we as a species can evolve. I mean, let's look at this Tycho Brahe. He basically kicked off the Enlightenment, right? And look where we are now. So who knows what the next couple of 100 years might bring if we manage not to kill ourselves with our technological capabilities in the next, 50, 100 years.
I agree. I try to be optimistic too. So I appreciate you bringing it back around. I didn't mean to end so dire. I think like putting it, yeah. you could put that in terms of like, I'm thinking about like, with specifically like the mRNA vaccination stuff. Like, yeah. I think there were a lot of times what I've heard when I came across people who were refusing to get it, a lot of them were saying, well, they're so new and I don't know much about them and I'm worried about possible consequences. And it's like all of that stuff to me, it makes perfect sense and it's perfectly rational and logical given their worldview and the frame set that they're given. And there is so much, it's so easy to distrust. So you're right. Like, I think that is something that that pace has quickened and accelerated, where I know so many people who were waiting when the vaccines first came out. They waited for 6, 7, 8 months, even up to a year. And now things have turned around because the science has come out and they have found some source that they can trust, because it is hard to believe that there is, like, if I jab myself with this needle with some mystery fluid in it, all of a sudden I'm not going to die if I become exposed to this terrible virus. That does take a level of belief and trust in institutions that may have otherwise been, perverted by other just human tendencies and things like that. So now we're at this point where there's this amazing revolution that people might not be able to trust at face value, but more and more people like you always focus on the negative and the small number of people that are vocal and against it, but just think of how quickly we were able to mobilize and distribute a vaccine to so many people who were willing to trust in science and put this mystery fluid in their arms, and how many lives have saved. Like we lost so many people because of this pandemic, but think of how many were saved because people did put their faith in science. So thank you for switching my worldview around on that to not be so dire about, focusing on the small minority that don't just instantly, believe or don't just just have that mindset that they are looking, they want to see what they see and not necessarily want to trust the science just right off the bat. But thankfully, I don't think many scientists were burned at the stake during this pandemic. So we have evolved to that point.
Well, not literally.
Yeah, just maybe on social media they were.
Yeah,
but
and on mainstream media as well.
Fair enough. Well, Alex, I think this was such a great conversation and it took it to a different. It took this to a whole different place than I thought we were going to go. But I feel so much better after having this. And like I said, maybe not even just that one section about transistors, but this whole last bit. I'm gonna save this in when I get down on life and on just people not trusting in science. I'm gonna rewind and come back to this. Are there any things you want to leave us with, or any thoughts that we can, or more importantly, how can people get in touch with you and follow you, what you're working on right now?
Well, that's pretty straightforward. I think I'm only active on LinkedIn, so that's where you find me. There's just one Professor Alexander Braun on LinkedIn, I think, and that's really the quickest way to look me up and what I do. I post regularly. So I do have a web page at my university, but that's not really nice right now. It's in the working. I've got a couple of PhD students who will hopefully work on that in the near future, but right now it's a bit barren. So
well, that's just fine. I mean, you can. I'm sure they're working on more pressing problems than if you need to spin up a WordPress site or something like that. It's put their minds to good use.
Well, yeah, and then pops they get some relief having an easy task like, okay, let's whip up our literature page to show to the world that we made a nice and interesting research. That's also important. Again, like this year, right? I mean, I think as a scientist, Harari, what's his first name? The historian.
I'm not sure.
Homo Sapiens is the book called, and Homo Deus. And that's, I think, Yuval Harari. He's Israeli. Love his books. I think he's really, really great. And he said a scientist who has an expertise in a certain topic has the obligation to share that at least a little bit with a wider audience. And that's what I'd like to do every now and then. It's not my main job, but we're sitting here. I like it a lot. I'm glad we have this conversation.
I am too. I'm really glad that our paths crossed the way they did, and I look forward to staying connected with you and hopefully having you back on at some point, because I think computer vision would also be something interesting to talk about. So let's stay in touch.
Autonomous driving. I'll tell you why we will not have a Tesla autonomous vehicle at the end of the year.
I've long, we have mutual friends in the automotive, automated vehicle space. And as I've been seeing the claims that Tesla makes and everything too, I'm like, it seems like it's that mythic. It's always 5 years away. Like everything in technology is always, if you just wait for 5 years, and I've been doing this for 5 years now, and it's the same promises that were being made for 5 years. And
yes, it is.
It's just going to be the next 5 years.
Especially autonomous driving. It's the year 2020 was supposed to really be the year where autonomous driving arrived. But to be fair, Tesla has a unique approach. No other company in the whole world has. It does have its own merits, but
yes.
I will, to quote Elon Musk, I will be shocked if they do have autonomous driving by the end of the 2022.
There you go. I love it. Thank you, Alex. I appreciate it so much.
Thanks, Tim, for having me again. It was great talking to you.
Thanks to Alex for joining Tim on the podcast today. You can connect with him on LinkedIn. Show notes for this episode can be found at constantvariables.co. You can get in touch with the show by emailing hello@constantvariables.co, or you can find us on Twitter at CV_podcast. Today's episode was produced by Jenny Karkowski and edited by the genuine Jordan Doust. This episode was brought to you by the Jed Mahonis Group, your go-to tech partner for Kick App, iOS, Android, and Rails apps and web tools that provide real business value and are enjoyable to use. Get to know us at jmg.mn.